So let's take a look at just this little PowerPoint exploring solids. It's pretty good.
Did you make it?
No, I didn't, but I made a couple little changes to it. Just skip that. So polyhedra. So a singular we call it polyhedron. Plural would be polyhedra. And poly means what?
Many.
Many. Anybody know what hedron means?
Sided object.
It does?
Yes,
Yeah.
studied this in roots. It's one of our roots.
Okay.
One of 375.
Okay. It doesn't mean face object.
Sided object.
I feel like you used that word. Okay, I think it refers in math specifically more to many faces.
Yeah.
So it's got many. So it's got many of what we call faces. Faces, and this is very specific, right? A polyhedron has to be bounded by polygonal faces. So faces that are polygons, two-dimensional polygons. So here's a face. Here's a face that's kind of on the front. You got to really kind of try to look at things three-dimensionally here. Those are faces. Edges are the boundaries between faces. The edges must. What do you think must be true of all the edges in a polyhedron? Well, okay, but even more generally than that, what would they all look like?
Brains.
Not lines, segments. Yeah. So all the edges would have to be line segments, right? Faces are going to be two-dimensional, be planar. Vertices are what vertices always are, right? Vertices are going to be where, in this case, the edges meet, right? So the intersection of the faces or edges, whatever you want to think of that. Okay, so we already talked about this. Vertex is where places where the edges meet. So which of these are, real quick, this is pretty easy stuff. Which of these are polyhedra and which are not? Yeah, A and C are, right? Yeah, C got kind of warped there somehow. So those are supposed, assume those are straight, because otherwise it wouldn't be a polyhedron, but pretend they're straight, so it would be. A and C are, B is not, how come?
Because it's curved.
Okay, because an edge is not a line segment there, right? It's curved, which we can't have. Okay, so this is how we describe them, and I want to kind of draw analogs between these two. So a prism is a polyhedron that has. Anybody want to hazard a guess as to what's unique about a prism? Think back, because I know you've probably done some stuff with prisms. What do you think, Joe?
There's multiple line segments that meet at one point.
Okay, that's going to be true. That's true. That's going to be true for. I think that's going to be true for all polyhedra. There's something unique about this one. What do you think?
It's where you take a two-dimensional object and you stretch it three-dimensionally.
Okay, that's one way to think about it. Is you're going to take a two-dimensional object and you're going to carve out space as you. Like I could take, for example, this book is rectangular, right? So think of the top surface of that book. If I were just to start it there and drag it through space, I would carve out a rectangular tunnel, right? That's a prism, okay? That's a prism. So more generally and more mathematically, what we can say is it's going to be a polyhedron where two of the faces are what we call bases, right? In this case, there's going to be a top base and a bottom base, and they have to be parallel and congruent. Okay? Does that make sense? So in other words, if I set this on a coffee table, the top, if I'm looking down from above, I'm going to see a triangle. If I crawl under the glass coffee table and look up, I'm going to see a bottom face, which is the exact same, right? Okay? So that is a prism. What do you think a pyramid is? How would you describe a pyramid?
One base and all of the edges meet at one point.
Okay, so it's got one base, and all of the edges have to meet at a common vertex, right? So it's literally kind of like doing this. I would take a prism, I'm going to take the top of the prism, all three of these vertices, and just scrunch them together into a single vertex, right? Does that make sense? Okay? So those are special examples of just a general polyhedron. Now, I'm going to come back to this. We'll come back to this in a second. Let's go forward just a little bit. So regular versus convex and concave. So a polyhedron is regular if all of its faces are congruent. Every face is identical, the exact same polygon, congruent polygons. Okay? It's convex Well, you tell me, what do you think, without looking at this, we've already talked about concave and convex polygons. So, kind of supercharge that for a polyhedron. What do you suppose a convex versus a concave polyhedron is? Okay, so, right, so if we could draw any segment that starts at one point on the surface of the polyhedron and ends at another point on the surface, okay, so, say it a little differently. If we extend any edge of the polyhedron, what's going to be, like, let's say I'm going to take, for example, this edge right here. Say I take this edge right here. And if I extend that edge, if it's convex, what has to happen?
Inside the polyhedron.
Okay, so it's never going to pass through the interior, right? Does that make sense? Okay, if it's concave, then there's a possibility at least one of those is going to have to pass through the interior somewhere, right? Okay, so let's look at an example. So this is concave, isn't it? Right? Because there's a whole bunch of them, but I could pick, for example, here's one. If I extend this one, look what happens. It passes through it passes through one of the faces of the shape, doesn't it? Right? That makes sense? So it's convex, or concave, sorry. Right? A concave polygon is going to have, or concave polyhedron, sorry, is going to have at least one of the faces that is a concave polygon, isn't it? Right? Yes, sir.
So couldn't you just say that in a convex polyhedron, all of the interior angles inside the polyhedron are less than or equal to 1
No, you can't say that. It have to be less than or equal to 180. Okay. It would have to be less than 180. That's a good idea, but it'd have to be 180. I see what you're saying. That's kind of, don't have to, I mean, I see what you're saying there, and it's true. But let's just stick it with the group. I mean, if that makes sense to you, great. Otherwise, just think of it as using our trusty old definition. Yes?
Would a pyramid be convex?
Pyramid would be convex, right? If we go back and look at the pyramid, see, there's an example of a pyramid, right? Any one of those edges that I take, if I extend them, they're never going to pass through. I mean, they're never going to pass through any part of either the surface or the interior of the polyhedron. Does that make sense? Like when they leave. So here's the edge. Whenever they leave these vertices, they're always going to be outside of the polyhedron. So therefore, it's convex, right? That makes sense? Okay, compared to this guy here, for which that is not the case. There's a whole bunch of lines that break the rules, or edges that break the rules, right? Here's one. That's the one we looked at. Here's another one, right there, right? As soon as it leaves in this direction, it's still traveling along the surface. Right? Even this one right here breaks the rules, right? It looks good at first. When it leaves up here, yeah, it's fine. It's going through space. When it leaves this vertex here, it's going through space until it gets to right there, though, and then it contacts the surface of the polyhedron again. So even that one breaks the rules, right? Okay. So describe this one. Is it convex? Yeah, it is. Is it regular? It is.
Yes.
Right? Because all of the faces are equilateral triangles, right? Okay. So if we take regular polyhedrons, then regular polyhedrons, here's an example of a regular, we call it tetrahedron. It's a regular, actually no it's not. Sorry, this is a regular octahedron. Okay. Because it's got 8 congruous faces. Right? What do you think is going to happen to these regular polyhedrons? And there aren't an infinite number of these, by the way. I mean, I shouldn't say there aren't an infinite number, but they're not very abundant. There aren't very many ways to create regular only certain combinations of types of faces that are gonna work, right? In fact, let's have a quick look. Let me just pull up, I don't think this shows this in our book, but let me just Google this.
There's a number file video on YouTube that's entirely dedicated to how many regular polyhedrons are possible in certain dimensions, like 6 dimensions.
Yeah.
Yes. Subscribe to the channel.
Have you seen cool 3D video on BuzzFeed yesterday?
How will I know the video if I haven't seen it?
Well, I don't know, I just can't remember the scenario.
I didn't just.
Okay, so just look at this real quick. This gives you sort of a representation. Does everybody see what's going on there? Those are regular polyhedra. And there are only so many of them, right? But what do you notice about the more sides that you get, what do you start to notice about the overall shape of the polyhedron? It's rounder, doesn't it? Right? And that's the important point I really wanted to make. Because now if we backtrack a little bit, the more sides a regular polyhedron has, the kind of rounder it gets. Let's go back to this page right here. This to me is an important one. So if we look at this, then we could draw, just, imagine one of those sort of roundish regular polyhedra, right? And imagine that's on the page also. Can you see a correlation here, right? Do you see that there is a correlation between these two,
Yes.
right?
Yeah.
And between those two,
Yeah.
and then between the sphere and one of the regular polyhedron, right? Okay, what is this? To me, this is really a cool correlation. How do you make that connection? Let's just take, for example, these two, right? If I were to take a prism, a regular prism, so a prism that's got a regular polygon for each face. So this is an equilateral triangle. If we move the number of sides up to 4, then it'd be a square base. Beyond that, it'd be a regular pentagonal face. You see what I'm getting at? Okay, how can you draw a connection between those two? How does a prism become a cylinder? Okay.
A cylinder is a prism with a number of sides.
Okay, right. So as the number of sides in the face, right, starts to get bigger and bigger, well then that face is going to start to look more and more circular, isn't it? Right? The bases are. When I talk about the face, I'm talking about the top base and the bottom base, right? Another way of thinking about that is the faces around the edge of the prism, and we'll talk about this in a second. We're going to call those lateral faces, because lateral means side, doesn't it? Right? You guys know that, right? Yeah. So the faces on the sides of this prism, as the number of those goes up, it's going to start to look more and more tubish, right?
But
And so all we're really doing, go ahead.
is it possible for it to become a cylinder?
Okay, so it's not, infinity is not a number, but this is one of the things we talk about in calculus, right? We can't say, let's let the number of faces actually be infinite, because that's different than saying let the number of faces be 64 or 50 or something, right? But what we could do is we could write it this way. We could say, let's take the limit. So we're going to take the limit of the number of faces, and we'll call it x, as x approaches infinity. Okay, that's how we would talk about that. You can't ever get there, but we could see what's the behavior going to be as the number of faces approaches infinity, and the answer is it would become a cylinder in the limit. Okay? And what's cool about this, and remind me about this, is your job when we're in calculus talking about the same problem. We could, at that point, we could say, okay, let's actually calculate what the area of a cylinder is going to be, starting with the area of a regular prism, and just taking this kind of limit. And what the math gods are going to show us is that as the number of faces, lateral faces, goes to infinity, the formula is literally going to become the area of or the volume, or whatever you're calculating, of a cylinder. Isn't that cool? That's kind of what math does, that you can start with a generic formula like that, where n represents the number of lateral faces, and you can do this trick, this awesome trick of taking a limit, and once you know how to do this, you can literally find out what the formula of a cylinder is from that, okay? And that's how do you think people actually got things like the area of a circle? Yeah, have you ever thought about that? How do you come up with the area of a circle? You take it for granted, right? You guys all know what the area of a circle is, but it's a pretty amazing proposition.
Our sphere's not real.
Well, I mean, nothing's real in a sense, but yeah, it's a perfect sphere, you've never seen one.
No, okay, so this actually has a video I thought kind of interesting. There's like the closest thing to a perfect sphere still wasn't even a sphere. Like it was the size of Earth, it would still be like 16 feet to the highest mountain. It's like that big, but
Oh, you mean that we built? Yeah, I got you. Yeah,
like that actually.
yeah, that's true. If you took like a billiard ball, for example, which seems pretty smooth, and you scaled it up to the size of the Earth, you'd have mountains that were ridiculously big. Yeah, it just would be. So you're right.
Oh, I get it.
Yeah, they were trying to base another physical object to base off of a kilogram, so it had to be the roundest object in the world, because that would count them in pounds.
So the roundest object in the world is
A
nothing.
gigantic metal ball that's a kilogram mass.
Same.
Yeah.
Okay,
Okay, so how do we find then this? And this is we'll talk about this in calculus also, but this is a really valuable thing to think about. So let's get our. I think I have to do it this way.
Oh, yeah.
Oops. So how am I going to find the area of that circle, do you suppose? Okay, well, that's what it is, but you guys, otherwise, people didn't know what pi was. That's the thing.
I would say just give up.
No, that's not a.
Measure it.
Ask Mr. Oya or Nick.
No.
Nick. I asked Nick what.
Oh, yes.
He doesn't like me, but he'll answer any question that I ask.
Yeah.
Literally. That's how he is.
Mr. Roy, isn't this what argument?
It is.
I asked him to explain to me
Didn't he use
why he thinks the
24
world is
sided
flat, and he
Lagos
tried to explain it.
Well, no, I'm not sure what number he actually used. It's not.
That's what Vsauce said. Why don't you bother YouTube?
Tell me, what now, pal?
A D10.
Yeah, Tyler, I know that basically all the things that you do in your life is video games, which
Yeah, but
we talk about this and stuff, and watch YouTube. That's it. Oh, and you play Breaks Under Brother.
no.
Okay, so that's close enough. Okay, so that's a regular. What is that? A regular octagon, right? Everybody agree?
It's a hexagon.
Okay, hang on, just listen. Okay, so that's a regular octagon.
It's a hexagon.
Is it?
Yeah.
Oh, you're right, regular hexagon. You're right, regular hexagon. I can't count.
I counted 7 and I was like, no.
Okay, I'm gonna do another one.
I think you need to look.
Let's see, find the area of one and then do the other.
Okay, right. So I didn't do that perfectly, but wouldn't you agree? Now we can calculate. People have been able to do this for a long time. It's not a huge deal to be able to come up with formulas to calculate the areas of regular polygons. So we could calculate the area of a regular hexagon. And so what we'd say that the blue one, because the blue one, it's like we took a regular hexagon and we deflated it until it bumped into the circle. Does that make sense?
Yeah.
Okay, so that's called a circumscribing hexagon. So we would say that it is the smallest circumscribed hexagon is the blue one, right? It's the one that just touches from the outside, it just touches the circle, right? Now the red one is different. The red one is like we took a baby regular hexagon and we inflated it from the inside until it bumped into the circle. So that's what we call the largest inscribed hexagon. The area of a circle has to be where? Somewhere between those two. Now, we don't know where though, but it's not going to be like it's halfway in between. It's just in between those two, right? What's going to happen though, so there's quite a bit of wiggle room there, right? I mean, there's, the red one is a fair amount too small, and the blue one is a fair amount too big, right? Could I choose a different kind of polygon that's going to work better?
Yes.
Well, okay, octagon would work better, and then what's going to be better than an octagon? Okay, something that's got more sides, right? But you agree that the more sides I have, the better the polygons are going to fit the circle?
Yeah.
Okay, so if we wanted to come up with the actual area of the circle then, what could we do to get the exact area? Any ideas?
Infinity is
Approaches infinity.
Okay, we're going to do the same kind of a trick. We're going to let the number of sides of the polygon approach infinity, and as that happens, the blue one is going to perfectly enclose from the outside the circle, and the red one is going to perfectly fit from the inside. They're going to merge onto the one single exact right answer, and that's how you come up with the area, actual area of a circle. Now you got to know a little math to know how to do that. There's some analysis there that's you haven't learned yet, but we'll learn how to do that stuff in calculus, right? So
really good at counting.
It's not fair. You study trig like every week. I mean, you like to go in the building that's on Wi-Fi.
okay, so then everybody see that we can make those connections, and a sphere is just going to be the similar. Well, a pyramid becomes a cone as the number of sides of the base goes to infinity, right? A sphere is going to be like a regular polyhedron as the number of faces approaches infinity, right? You get the idea? And so all of the discrete ones become the smooth ones using calculus, using limits. Okay?
If you put sphere inside and a cone inside a cylinder, the sphere and cone fit perfectly with one another?
The sphere and the
If they have the same, like, if the circle had the same circumference as the
Well,
cylinder.
the cylinder.
One thing.
You mean inside the sphere? You mean?
Can you put the sphere and the cone inside a cylinder and they're all the same weight?
No, they would have to be slightly smaller, right?
Well,
No.
the answer is no, you can't. But that's an interesting question. Like you'll get that question in my calculus class. What I'm going to ask you in my calculus class is something like, if you had a sphere of radius 10, what is the volume of the largest inscribed cylinder? And you'll be able to tell me. Okay, so that's, yeah, but that's still 3 years away. So we got a little ways to go.
Are we gonna be taking pre-cal on junior?
Yeah.
No, pre-calc trig.
We got tricky. Okay, so we've already talked about this stuff. Last issue, I want to show you one more thing. So what about this one? Is the octahedron, so it's got 8 sides, is it regular?
No.
Okay, no, now,
No.
it's not a regular octahedron. We could say that it's a regular prism, right? Because the faces, the lateral faces are all congruent, and the two bases are congruent. That's different. If we just take this as just a normal 8-sided, because it's got 8, right? 1, 2, it's got 6 lateral faces and 2 bases. But obviously the faces and the bases are not congruent. And so taken as an octahedron, it is not regular. Okay?
Why would it be an octahedron if it has 6 sides?
Well, it doesn't. It has 6 lateral faces and 2 bases for a total of 8. Okay? Convex but non-regular. Same thing here, right? Obviously that's not
So
regular.
convex can be regular, but I mean, but the other one, concave.
Concave
can't be.
never could. You're right. Concave never could. So that's concave and non-regular. So now, next issue is cross sections. So we do this a lot in math too. A lot of times we take cross sections of 3-dimensional objects. In fact, there's something that I don't currently teach in calculus, but I will for you guys, I'm sure. It's called analytic geometry, and it describes all smooth shapes as being cross sections of a cone, and that's interesting. So you can do that. So you can take ellipses, circles are just perfect ellipses, parabolas, and even hyperbolas, and those are all, we'll see when we get there, that those are really just different cross sections of an infinite cone. Okay? And so if you understand that they're all related to a cone, it helps understand how the different ways of describing those are all really very, very similar. Yeah.
What is the name of the shape of the track?
The shape of the track, okay, it's a composite shape is what it is. It's a combination of, a track is just you take a circle and you split it in two, and then you enclose a rectangle with that. So it doesn't have, it's just a composite shape.
Because I call it circle running, and then he says it's not a circle.
It's not a circle.
It's not.
That's right.
What if it's
I don't know what it's called.
would it be an ellipse because it's just,
No, it's not a true ellipse.
Because it's straight.
oh yeah.
She's got straight sides too. Okay, so let's look at some of these cross sections. What is this cross section going to look like?
Two rectangular prisms.
So if I take a cross section of what we would call, this is a cube, okay? Cross section of a cube. If I make the cross section parallel to one of the faces, it's going to be a square. Does everybody see that? Okay, now what if I were to tilt this though? What if the cross section went through at an angle?
It'd be a straight rectangle.
It'd be a rectangle. Okay, what? Did everybody see that? So if I tilted it down like this, I'm going to end up with a rectangular cross section. This takes a little thinking. What if I did this though? What if I came in from I went at an angle, but not approaching one of the faces directly? What if I went at an angle diagonally?
Triangle?
No. Well, I could get a triangle, but if I went all the way through the whole thing, what would I get? No.
Irregular?
I think it's square.
So if I did, it's really hard to visualize, but say I took this, say I had an infinitely long, like, piece of ductwork, right? So it's just going to be, it's got a square profile. So, it's just like a ductwork. It's like where air goes through ducts. So it's a square profile duct. So a cross section parallel to the floor would be square. So if I go through the duct, and here's going to be my duct, let's say. Okay, if I go through the duct like this, if I go through like that, it's going to be rectangular, isn't it? Right? But what if I go through like this? What if I take, yeah, you guys are back over. What if I cut like this? No, but it's infinitely tall.
It would be
Like a
Yeah,
diamond?
what's that? What is that called? A rhombus. That's it. Exactly. It'd be a rhombus, wouldn't it? Right? Okay, now what if I cut one so it goes through diagonally through a corner?
Oh, triangular.
Triangle.
Give me an equilateral triangle. If I go to 45 at least, right? Okay, so there's a bunch of ways I could do this where I'm going to get some weird things. What if I went through, how about if I cut through so the shape, it cut through the base down here. Think how, so it's going to come out like right here. Hang on a second. So no, it doesn't go out there. It goes in, goes out. Say it goes in like right there. So then I'm going to have face there, and a face there. What could that be? I mean, it could be something weird, right? It could be a trapezoid. Everybody see that? Right? If I went through at the base where this is a little wider than it is up here, my point is you get all kinds of geometric shapes out of this thing, right? Okay? All right. Okay. Okay, oh, there's some pictures, right? How about that weird one? So now I'm getting some kind of bizarre, what is that? 1, 2, 3, 4. That's a pentagon, right? Okay. Triangle. Okay, so there's all kinds of weird ones you could get.
That's a really weird.
So here's our definition. Polyhedron is a three-dimensional solid made up of plane faces. Prism is a polyhedron that has two parallel congruent faces, right? All of the lateral sides are going to join to those. Okay. Tetrahedron just got 4 faces. So this is a regular tetrahedron, right? Because it's got 4 congruent shapes for faces, right? 4 congruent equilateral triangles. Yeah, go ahead. Okay.
Why are there so many different words like quad and tetra and whatever?
I know it's kind of annoying, isn't it? The quadrilateral has 4 sides, but tetrahedron is.
We should have one language.
I know we need to.
Quad
I
is
tried
Latin,
to do that
tetra.
once, and that didn't turn out well, because no one.
Okay, so there are only, and this is kind of interesting, there are only 5 regular polyhedra that actually work in 3 dimensions. They're called the Platonic solids. And here's some examples, right? There's a cube. A cube is just a regular hexagon,
This is what the
Right.
number file video is about.
okay, and then here's a regular octagon, right? It's like joining 2 regular tetrahedrons together, gluing them together. A regular dodecahedron, a regular isosahedron, and then there's one more, which is they don't show. Okay. Oh, well. Okay. Euler. Euler's how you say his name. Okay, now here is, let's go back a little bit. I want you to see if you can, close your eyes. Okay, go back to this real quick. See if you can come up with there's the other one, regular tetrahedron. There's the 5th. Okay, see if you can come up with a formula. And these don't have to be regular, by the way. So if we look at a regular tetrahedron and we counted all of the parts of this, we would see that there obviously are 4 faces. There are 4 vertices in this case. And there are a total of 6 edges. Can you kind of count those in your mind there? Here, the 6 would just be like 3 along the base, right? And then plus another 1, 2, 3 for 6 total.
Now, I feel
Okay.
like faces plus vertices equal edges plus 2.
Okay. You saw that, huh? Okay, so let's see if that works. Here's the hypothesis. Faces plus vertices equals edges plus 2. See if it works here. So here we've got a cube. So faces plus vertices equals edges plus 2. It works, doesn't it? Yeah, where'd you find that?
Oh, yeah, I knew that.
That's pretty good.
Oh,
Yeah, right up there. That's good. Okay, how about a regular octahedron? Faces plus vertices equals edges plus 2. Yeah. Plus 2, right? Regular dodecahedron. Faces and vertices add up to 32, so 30 edges. 30 plus 2. It always works. Sure. That'd be the same thing. So this is Euler's theorem then, right? So the number of faces F, vertices V, and edges E is always given to us by that formula.
Why is that his name? What? Euler?
Euler.
Why is that's not?
That's how you say it though.
Euler?
Wait, how come you aren't a college professor?
Because I teach high school.
Yeah, for real. You make really money.
No, I like teaching high school. So here's a weird one. This one, notice this is not, it's not regular, right? But if it's got 14 faces, 8 triangles and 6 octagons, you could figure out how many vertices it has, right? If you just count, the relationship is still going to hold here. It's got a total of 14 faces. You could count the number of edges and and we could do it pretty easily actually, right? Because each of these triangles, how many triangles are there total? Be 8 total. So 8 times 3 is 24, right? Then how many additional segments are there going to be? Well, there's going to be 4 on the top and 4 on the bottom and 4 around here, right? Additional segments.
No, because then it'd be only 2, because then you'd have one of them.
Well, let's take them off. So on the top we'd have that one, extras, right? Not the ones taken up by the triangles. So we got this one, this one, this one, and this one, right? 4. Okay, well, no, not quite, because now I've got a bottom face that's going to be exactly the same. 4 along the bottom. 1, 2, 3, 4 down there, right? And then look, I've got 1 there, 1 there, 1 there, and 1 along that back vertical edge. Oh, I got you. Okay. So we've got 8 times 3 is 24 plus 3 times 4 is 12, right? So what do we get? What is that? 36? Is that right? So if we want to know the number of vertices, then all we have to do is just use this formula, right? We said the number of faces was 14. The number of edges was, did we add it up right? Did we say it was? 3 times 8 is 24 plus 12. Yeah, so it's 36, right? edges is 36, faces is 14. What's the number of vertices? Edges was 36, so 38 on this side, and there were 14 faces, so 38 minus 14, right? 24. Gotta be 24 vertices then. Okay? Okay? You get the idea? 24. Okay?